Hi everyone, thanks for coming along to my talk today and welcome to GPCE. My name is Bruce Collie and today I'm going to be talking to you about some work we've recently done at the University of Edinburgh on modelling black box software components using probabilistic program synthesis. So first, let's talk about what we mean when we talk about black boxes and black box software components. Put simply, a black box component is any piece of a software system whose internal details are totally opaque to analysis. We can observe the behavior of the component by passing it inputs, which it maps to outputs through some transformation. However, we have no knowledge externally of what the semantics of this transformation or how it's implemented. In this paper, we demonstrate a new method using probabilistic program synthesis to extract a programmatic executable model from black box components with minimal prior information. It's worth also taking a second to think about the reasons we have for thinking about black box components as opposed to those which we know more about. For example, if we were to have access to the original library source code. For example, components in this abstract library here could be implemented by calling out to specialized hardware or across a network service, or they might be distributed as compiled binary code only. In each of these cases, while it's desirable to be able to model the behavior of the component, we don't have access to the original source code to do so. And in each of the cases, we'd still like to be able to recover the underlying behavior. Here in this case for component G. Additionally, it's worth noting that considering black box components gives us a minimal problem statement. The scenario we're operating under might seem draconian, but it gives us a starting point to build up more complicated scenarios on top of the black box component specification. With that context out of the way, and I'll give you a quick overview of what I'm going to go through in the rest of this talk. First, I'll explain how we built Pressin, a program synthesizer that aims to recover program implementations from this kind of black box oracle. Then, I'll explain how we built a dataset from program synthesis literature of benchmark programs and used it to compare Pressin's performance to other leading program synthesizers. I'll also explain how we used Pressin's results to obtain insights into the benchmark suites and what the programs in them look like. Finally, I'll explain some use cases for this kind of black box analysis and why it's useful in software engineering applications. So now, let's go through our implementation of Pressin, our program synthesizer targeting black box oracles. The first thing we need to think about is how to state problems in program synthesis and what inputs are given to the synthesizer. Pressin takes two pieces of inputs for a given problem: a type signature for the computation being performed by the black box it's targeting, and an opaque library containing the implementation that we can make calls to. These are the only inputs that Pressin requires. Next, we have to think about correctness of potential solutions to the synthesis problem and what it means for them to be correct. For a potential solution, the question we're really asking is, does it correctly model the behavior of the underlying black box? And the only way we can tell this is through external observations of their behaviors. And so observational equivalence is the only way we have to determine correctness of potential solutions. We check observational equivalence by generating many random input data points for the black box, then calling the black box to generate the corresponding output data points. We do the same for the solution program to create corresponding outputs. Then we check if each black box output is the same as the corresponding solution output. If they are, then the two are observationally equivalent and the solution is correct. Now that we're able to specify synthesis problems and test whether potential solutions are correct, we can talk about how Pressin actually builds up a program. Broadly, Pressin synthesis falls under the umbrella of sketch-based program synthesis, where solutions are built up compositionally from smaller parts or fragments. In our case, fragments are individual atomic elements of programmed structure, either control flow or data flow, and we can think of them as essentially partial ASTs. On the left, there are some illustrations of what we can visualize fragments as looking like. Circles represent concrete code, while squares represent potential points for further composition. Preston uses a library of 11 different families of fragment, which are arbitrarily composable to form sketches. Fragments are also representable as code and can be compiled into a program at any stage in the composition. For example, the highlighted fragment on the left might compile to code looking something like the right-hand side. Solutions, or the structure of solutions, are built up by composing fragments to produce sketches within Preston. This, of course, raises a question for our synthesizer. How do we know which of our library of fragments will appear in a correct solution to a particular problem? And how do we know how to compose them to produce that solution? The space of potential compositions is very large, and to avoid a combinatorial explosion, Preston uses two probabilistic models to predict the most likely fragments and compositions of fragments to appear in a solution. The first of these models simply aims to predict which fragments are likely or unlikely to appear in a solution. At the top of the slide, we've got 6 example fragments. These fragments are passed to a classifier along with the type signature for the current synthesis problem. This classifier makes a binary decision whether the fragment is likely or unlikely to appear in a solution. Note that this can't be 100% accurate, and so we keep the unlikely fragments around. The second of Preston's 2 probabilistic models aims to predict from these 2 sets what composition of fragments is the most likely to produce a correct solution. To do this, we use a Markov model. Our semantics for fragment composition permit a linear representation of any composition, and so we can use Markov models to generate sequences of fragments that represent composed sketches. This model can be used to generate compositions or sketches from most to least likely. This allows us to prioritize our onward synthesis process towards compositions that are more likely to produce a correct solution. These models were chosen for Preston because they're easy to train, and we do so using observations of correctly synthesized programs. To obtain the results in the paper, we used a 15% split of our evaluation set of programs, which I'll discuss later, determined randomly and annotated by hand with the ground truth fragment compositions that were used. This process can actually be done without upfront training data, but for space reasons we didn't include these results in the paper. Preston can operate in a stratified mode where synthesis of many programs is attempted in parallel, and the results from early successes are used to inform the models for later syntheses. We hope to elaborate on this in future work. These 2 models produce sketches, which represent only the structure of a potential solution. In the final stage of synthesis, Preston instantiates sketches into executable programs. On the left of the slide, we've got an example sketch shown visually, and on the right-hand side, we see the pseudocode corresponding to it after it's compiled to code. Fragments specify holes within their structure that represent places where values can be selected in the final instantiation. On the left-hand side of the slide, these are question marks in the pseudocode. In the final stage of synthesis, we use an iterative hole refinement procedure to select concrete single static assignment values for these holes. As types are chosen for holes, constraints are enforced on other values and their types. We use a heuristic-driven enumerative search to search through the space of potential instantiations and identify correct candidate programs. So that's the implementation of Pressin, our program synthesizer for black box Oracle. Now, I'd like to show you some of the results we've obtained from using Pressin in practice and explain how we compared it fairly to other program synthesizers. Our key evaluation question is, how does Pressin compare to other program synthesizers? We identified 4 leading program synthesizers, each with a different implementation and target language strategy. These were Makespear, a genetic-based program synthesizer, Lambda Squared, a functional type-directed synthesizer, Simple, which synthesizes imperative programs, and SketchAdapt, a neural approach to program synthesis. Unfortunately, our evaluation question is somewhat loaded. Comparing program synthesizers against each other has been identified as a challenging program in the literature for a number of reasons. Synthesizers have different type systems, target languages, assumptions, synthesis vocabulary, and target domains. All these differences mean that there's often a large impedance mismatch between synthesizers that makes a fair comparison difficult. To address this problem, we compiled a large set of benchmarks that can be used to compare all of the program synthesizers we identified. Our benchmark collection comprises 112 different functions, taken from a lot of different program domains. For example, mathematical functions, string and array processing, and synthesis benchmark problems taken from existing literature. Additionally, we augmented this set with functions from existing well-known software libraries. We normalized these benchmarks so that they could be run on any synthesizer we identified. Unfortunately, this means that the results we obtain aren't identical in all cases to the original paper's results. This is because some functions had to be discarded, for example if they used functionality that was unique to a particular synthesizer or that couldn't be replicated fairly across all of them. We ran each synthesizer and all 112 functions from this benchmark set and recorded how many each synthesizer could correctly synthesize. We examined 2 scenarios for this benchmarking. The first aims to replicate the conditions used in the original paper, where some prior information is given to each synthesizer, for example a partial program sketch constructed by hand, or a set of recursive base cases, or similar information. The results from these scenarios are shown in orange, and under these conditions the best performing synthesizer we compared Pressin to synthesized nearly 50% of the benchmark set. However, Pressin requires very little prior assistance to synthesize functions, and so we compared each synthesizer also under similar conditions to that Pressin requires. These results are shown in the blue bars, and we see that the other synthesizers are able to synthesize far less of our benchmark set under conditions similar to Pressin's. We also compared to TypeDirect, a previous version of Pressin we describe in prior work. The results show that Pressin is able to significantly improve on the synthesis performance of these other implementations while requiring less prior knowledge to begin its synthesis. As well as these promising synthesis results, we used Pressin's learned models to get some interesting insights into the structure of the benchmarks we evaluated and where synthesizers succeed and fail on them. For example, we looked at the distributions of fragment types encountered in each set of benchmarks. We noted that Makespear and SketchAdapt, the 2 most difficult sets of benchmarks to synthesize across all implementations, exhibited the greatest variety of different fragment types. We found there was a good correlation between the variety of fragment types and the difficulty of synthesis. Additionally, some intuitive ideas about the structure of each library pop up in these results. The BLAS benchmark set's prevalence of looping fragments points to the high incidence of nested loops in the programs in that suite. Finally, we performed 2 short case studies to identify practical applications of synthesis from black box oracles to real-world automated software engineering tasks. Our first example is providing automatic portability for applications using synthesized functions. We do this by inlining the synthesized function back into its call site in an application. If the original function, the black box, was implemented such that it was in hardware or in a network call, inlining the synthesized code provides a portable version of the application that can be recompiled for any target. Additionally, we performed some search-based software engineering tasks using a tool called Candle. Candle allows us to search for particular idioms or instances of patterns within compiler intermediate code. We converted our synthesized programs to this representation and used them to search for re-implementations of code within an application, as well as for API migration opportunities between two libraries. Thanks for listening to my talk. I've discussed how we can build a program synthesizer for black box oracles and why we're interested in black box oracles in the first place. Our implementation, Pressin, provides state-of-the-art program synthesis performance on a large, challenging benchmark set that provides a compelling cross-evaluation of 5 different program synthesizers. Thanks for listening, and I look forward to your questions.